processes look like. This one's called, Josh and I just dubbed it the jump normal distribution. So it's a compound Poisson process with the values drawn at the jump time. And basically, how you can think of this is at the center, that's the value of the process at some time. And how easy is it for the particle to get from here out into the tail? So a model that has heavy tails says large things can happen in short amounts of time. These two processes are on the same scale, which means they have effectively equal variance per unit time. But this jump process, you can see, has fatter tails and a narrower peak. So these jump processes, one quality I would say they have, they're sort of deliberate. Either nothing happens or something happens. It's not entirely predictable when that something happens. So one of the next parts to this is trying to discuss what could these jumps possibly mean. So I think few people would think that evolution is driven by these rare mutations of large effect. It's more likely to be something that is these rapid shifts, these jumps seem to resemble sort of rapid adaptive shifts in sort of a Simpsonian sense between different adaptive zones. And how could we argue about that? Well, adaptive shifts do seem to complete rapidly in deep time. So once a shift begins, it'll wrap up, depending on different types of theory, on the order of, say, 100 to 1,000 generations. So here's a nice model, some theory in '82 by Mark Kirkpatrick. You have one optimum here. Let's see if we can get that right there. Another one over here. And over time, this population with its phenotypic variation is transitioning from one optimum to another. So what is the amount of time here that transition takes? That's one question we're interested in. Well, in this particular paper, these two means are separated by on the order of 3 standard deviations, something like that. And under this model, it took approximately 3,000 generations to complete. And if you compare that number 3,000 generations to say 3 million generations, or say 1/1,000 for the tree height, perhaps an instantaneous jump isn't so ridiculous. Also, this is the same 3,000 generations. I just fixed the width of this. Maybe that's, yeah. Okay, maybe that doesn't work exactly. But in any case, this is 3,000 generations. This is a fossil time series in a nice paper by Gene Hunt and others where they're looking at stickleback morphological evolution. This shift seems to begin at the shift does begin at generation 0, and it appears to complete around generation 3,000. So now we have some microevolutionary theory, and probably one of the only good examples in the fossil record of actually capturing one of these shifts. And there is a coincidence in terms of the numbers of generations. It doesn't mean that how it has to work out, but it's interesting to me at least. Okay, now the last thing is that this is the price of gold in terms of, I forget what it's called, there's some strange unit they use for ounces in gold pricing. I'm not sure if anybody's like what's it called, a prepper, where you're worried about the apocalypse and you want to have hard currency. But these are just some prices I lifted for the past 4 years. And people in Wall Street are quite literally investing in the results of their models, right? And so they care very much about whether or not they can capture these jumps. And these jumps are crucial to explain this parameter that they term volatility, which is essentially how much change can occur in a small interval of time. Another thing that's worth noting is that this is a very nice fossil record. Now, unfortunately, the fossil record we actually have is a little bit more sparsely sampled. So instead of, say, this is going to be literally thousands of fossils, perfect time intervals without any type of taphonomic bias or anything of that sort, well, except for insider trading. But here's another nice analysis by Gene Hunt and others, where they're looking at fossil time series here, and they show that punctuated change is relatively common so long as you have enough samples. So if you have enough data, you seem to be able to find this pattern. So this project that Josh and I endeavored on was basically to ask, are these bursts using very simple models common in macroevolutionary data sets? And then we sort of asked three basic questions, and this follows the tradition that others set forth previously. But first, can we measure the model? Second, is that mode selected frequently? And third, are the measurements realistic? These are the people that we followed. This is a preprint that we put up on bioRxiv recently. I'll have this as the last slide. Here's code for some of the models that we use that includes optimization methods. I'm going to have to speed along a little bit here. The method that we use isn't measurable. We use independent contrast. Independent contrast works like this. You have a tree, you know the values of the tips, you know the branch lengths, and once you prune the contrast, basically find a phylogenetically independent contrast, prune it from the tree, and replace that with a pseudotip, something that says, hey, I don't know exactly what this value x6 is, but you should know that it's not a precise estimate of that value. You can then decompose the tree recursively, so you have all your contrasts here, and then wonderfully you have these independent contrasts you set to take the product of them, and there's your model likelihood. Now, the problem with these Levy processes is you cannot compute this quantity analytically for most Levy processes. One nice thing is that Levy processes have this form using these characteristic functions. This is gobbledygook, but here there's two important parts. You have the amount of evolution that occurs on the left branch, the amount that occurs on the right branch, the amount of that pseudotip error that accumulates on the left, the amount that accumulates on the right, and that gives you this nice characteristic function. Once you have that, you can use the Fourier transform, get the probability, and now we can get that. Now we can do that product of probability. So that's just a super brief overview of what we're doing. This project actually sort of began about 6 or 7 years ago, where we first read this Harmon et al. Paper, and we just absolutely loved it. But when we tried to reproduce some of these support values under Levy processes, we found that we simply didn't have enough data to inform these complex models. And so we revisited this paper, including a model of this punctuated change that I just described, the Levy processes, including a parameter that estimates the variation at the tips, and reanalyzed it. And this to me is just one of these projects that seemed to be ahead of its time. The data set we used, just briefly, had 66 clades, about 8,000 species. We used a variety of ways of collecting trees, both super trees, meaning pruning out clades or collecting individual clades. We had length and mass measurements, about 126 taxa per clade on average. Here are the models that we fit. We're going to compute the AIC, a model fitness statistic for all those models. And all these models also include a parameter for interspecific variation. I'll get into that detail in a moment. So suppose that, this came out funny, but suppose that we only looked at this incremental wandering process, the Brownian motion, and the explosive model. Suppose we looked at all models except for the one with punctuated change, the Levy process. This is the type of AIC, the AIC weights that you get as profiles across clades. So we tend to get strong support for Brownian motion, strong support for early burst, weak support for OU, and quite a few undecided models here. If we then do inference under these Levy processes, we now have the plurality of support for these Levy processes that siphons away some support from early burst and Brownian motion. We have approximately the same number of undecided processes, but this block here are clades that seem to prefer the Levy model. And remember, these are all very parameter-light models. We're talking